All right, everyone. We were looking on Friday, on Friday, page 63, some questions that we didn't have a chance to finish up. I want to go over those questions now, 14, 15, 16. 14, we were in the middle of Friday when the bell went, and we kind of finished it off, but not really. So let's take a look at question 14 a little bit better than we did on Friday, and then let's look at 15 and 16 as well. I remember this. It said, 14 said, a person in an apartment building is 5 meters above the person walking below. She drops some keys, but then there's a guy that's below that has to walk to catch them. So we've got kind of two things going on. We've got the keys falling this way, then we've got the guy walking this way. They have to meet up. Two problems. In this problem, we know that A is negative 9.81 meters per second squared. In this problem, we know that VI is 0 meters per second. And in this problem, we know that the displacement is what? How far do the keys have to fall for this guy to catch the keys? Yep. Not 4.75, but 3.75, right? The building is 5 meters above the ground, but he's catching them 1.25 meters above the ground. So the keys don't need to fall 5 meters. The keys only need to fall 3.75 meters. So the displacement will be negative 3.75. All right, now let's look at the guy walking. The guy walking has a velocity, a constant velocity of 2.75 meters per second. That's all we know. We want to calculate how far he has to walk. Pretty hard to solve for delta D, solve for anything, given only one variable, but we'll get another variable in just a second. Here's the key. These keys fall 3.75 meters for a certain amount of time. The guy walking in green there has that amount of time to walk that distance or that displacement. Let's figure out how much time that it takes for these keys to fall, and then let's take that time and plug it in down here as another given to solve for the displacement of the guy as he's walking. So let's do that now. Let's say for the fall of the keys, D is equal to VIT plus 1/2 AT squared. And listen, if you're not sure, if you don't see this strategy when you first start this question, that's okay. You don't have to know exactly how you're going to solve a problem when you start a problem. Okay, what you can do if you're not sure where you're going with this is just do something that is valid. Analyze the fall of the keys. Get something. Even if you don't know what you're going to do with that something, get it anyways. Because it's amazing how sometimes that light bulb goes off in the head after you've solved for something. After you've solved for the time that it takes the keys to fall, let's say. It's amazing how all of a sudden that it just comes to you sometimes. What do I do with that? Okay. Use it for the guy walking. This is 0. Let's rearrange this to solve for t. The 1/2 a goes down by dividing. And t becomes the square root of delta d over 1/2 a. So we're going to say the square root of negative 3.75 divided by 1/2 of negative 9.81. Let's do this on our calculator as a group here. Let's say neg 3.75 divided by, let's use some brackets here, 0.5 times negative 9.81. 0.76. Let's square root that. Oops, we didn't square root that. Now let's square root it. We get a time there of 0.8744 seconds. 0.8744 seconds. Now, we talk about sig figs sometimes. We don't round this to the right number of digits because this isn't a final answer. We keep that unrounded to 4 or 5 decimal places. That's how long the keys fall. That's how long this guy walks. So we've just got another given provided to us. Now, for the guy walking, since he's walking at a constant velocity, let's use d over t, rearrange it. T goes up by multiplying v times t. He walks at 2.75 meters per second for a time of 0.8744 seconds. Now, it's an easy problem, right? Just multiply those two numbers together. 2.4 meters. So how far does a guy have to walk in order to catch these keys? He has to walk 2.4 meters horizontally to catch the keys. Does that make sense? Listen, if I give you a question that said, how long does it take the keys to fall 3.75 meters, you'd get that, right? If I gave you a question that said, how far does a guy walk if he's walking at 2.75 for 0.8744 seconds, you guys would get that. So what's the difference here? It's just two problems in one. Okay, we just got to recognize in this question and other questions like this, there's two things going on. There's the fall of the keys and the guy walking. We can't analyze those together. We've got to do it separately. What quick little question though. This displacement for the vertical, for the downward motion of the keys, did not translate to the displacement of the horizontal, the guy walking. The velocity for the vertical did not translate to the velocity for the horizontal. The acceleration for the vertical did not translate to an acceleration for the horizontal, but the time did. Why is it okay to make the time the same for downward motion and horizontal motion, but not those other variables? Why is it okay to move over the 0.87 from the y-axis motion to the x-axis motion, but it's not okay to move over the displacement or the acceleration or the velocity? It's actually a simple answer here. You might not be thinking of it right now, but it's a pretty simple answer. Yeah. Oh, you started saying a word. I thought you had it. Yeah. Because time's a scalar. It doesn't have a direction associated with it, right? So whether it's downward or horizontal, it doesn't matter. Time's a scalar. There's no direction associated with it. Well, we can't take the vertical displacement of 3.75 and put it in the horizontal because the direction matters. It's 3.75 downward. It's not 0.87 downward. It's just 0.87. Right? Does that make sense, guys? That's why we're allowed to do that with time, but not the other variables. Okay, we had two more questions that we needed to go over from that page, 15 and 16. 15 said a rocket launched vertically upward accelerates uniformly for 50 seconds until it reaches a velocity of 200 meters per second up. At that instant, its fuel runs out. Calculate the rocket's acceleration. Calculate the height of the rocket when its fuel runs out. Explain why it continues to gain height for 20 seconds after its fuel runs out, and then calculate its maximum height of the rocket. This is a hard question too. And you know what, guys? Just like the last one, there's really two problems in one here. There's the phase of the rocket going up as it burns fuel, where there's gravity acting, but also the rocket acting. And then it runs out of fuel. As it continues to go up, it's just gravity acting. So we got to treat that as really two separate problems, right? The part where there's gravity and a rocket acting, and then the part where there's just gravity acting. Let's write down some givens here. For the first stage, we're going to say VF is 200 meters per second. Right? The rocket accelerates this thing to 200 meters per second for a time of 50 seconds. How fast was the rocket moving when it took off? Yep, 0. VI would be 0 meters per second. We want to find the acceleration. Now, in the second stage, after the fuel runs out and it becomes just gravity acting, we know a couple things about that one as well. We know that it goes for 20 seconds after the fuel runs out. We want to find the maximum height. So let's say VF for the second stage is 0. Do we know what VI is for the second stage? How fast is it moving when it begins that second stage, Stephanie? 200 meters per second, good. At the end of the acceleration phase, the rocket phase, it's moving at 200. So that's the beginning of the slow down phase, moving at 200. Yep. Good. And acceleration would be negative 9.81 meters per second squared. Because at that point, the rocket's no longer doing anything, right, other than going up into the air like a rock would. Okay, let's do the first part. The first stage for the acceleration. We're just going to say, I think, delta V over delta T for this one. Final minus initial velocity. 200 minus 0 over 50 seconds gives me 4.0 meters per second squared. Question B, the height when it runs out, let's just say D is equal to, there's a couple options here, VI plus VF over 2 times T. That's going to give me 5,000. We're going to round that to 2 digits, 5.0 times 10 to the 3. 2 digits because of this, right? Least significant piece of data. So at the end of the first stage, this is how high it is. Hey, question C, this is just a why question. Who can answer that one for me? Why does the rocket continue to gain height for 20 seconds after its fuel runs out? Why? Yeah, yeah, that's good enough for now. Momentum, he said, because of its momentum. It's more because of its inertia. Momentum works too, actually. But you don't really know clearly what either of those terms mean right now. You guys have heard them and you can kind of use them. It's not until later on in physics 20 that we talk about inertia. And it's not until physics 30 that we talk about momentum. But yeah, loosely, yeah, because it has momentum, it has inertia, right? It wants to keep going. It's moving. When it reaches the beginning of that second stage, it's moving. It slows down because gravity acts on it, but it doesn't stop instantly. Gravity doesn't make things stop instantly. Question D, the maximum height of the rocket. Let's say D is equal to VI. Actually, let's go VI plus VF over 2 times T. VI, now remember, this is after the rocket stops burning. This is just during the gravity phase of it. VI is 200. VF is 0 because it stops at the top. During the gravity phase, the time is 20 seconds. So my answer is what, 2,000 meters? Who agrees with that? Who agrees that that's the right answer? Who disagrees that that's the right answer? Oh, I've got a couple people disagreeing. All right, good. Seth, what's the right answer? If 2,000 is the wrong answer, then what's the right answer? Why not? Why isn't it right? Okay. 7,000 meters. Look, what have we just found? We've just found the displacement during the gravity phase. But it was already 5,000 meters above the ground. So we got to add that to the 5,000 meters. Works out to be 7.0 times 10 to the 3 meters, or 7,000 meters. How many people got 7,000 for that? Good. That's a tough question. Okay. All three of these are 14, 15, 16, all tough questions. Good questions, though. All right, 16, finally, it says, a ball is dropped from a height of 60 meters. A second ball is thrown downward 0.850 seconds later. Both balls reach the ground at the same time. What's the initial velocity of the second ball? Hey, I would bet that some of you looked at this question and said, what? How am I supposed to even start this question? Well, there should rarely be a time when you don't know how to start a question. If you didn't get this, that's okay. It's a tough question. But there should never really be a time when we don't know even where to begin a question. Okay? There's two objects moving downwards here. Object number 1, object number 2. Let's write down some givens for both of them. Okay? You can start with givens. Object number 1 falls 60 meters, so its displacement would be negative 60 meters. Guess what? Object number 2 also falls 60 meters. So let's make its displacement negative 60 as well. Object number 1 accelerates downward at negative 9.81 meters per second squared. So does object number 2. Object number 1 is dropped, so VI would be 0 meters per second. Object number 2, we don't know what VI is for number 2, right? It's thrown downward, number 2 is. So it does have an initial velocity. In fact, that's what we're trying to find, right? We're trying to find VI. Whoops, let's use green for that. We're trying to find VI for the second one. Anything else we have? Yep, Jacob? Okay, so let's say that this time, we don't know what the time over here is, right? Okay. But let's say this time is, Carrie? So let's say it's this time, the blue time, plus 0.85. Oh, you're so close. How about minus 0.85? That makes sense? It fell for a little bit less time than the blue one did, right? Because it was thrown down afterwards. Now, you could just as easily say over here, this time was the second time plus 0.85. Doesn't really matter how you do it. Okay. Let's call this, by the way, it's going to start getting a little bit confusing. Let's call this T1. Okay, let's, sorry, T2, I should say. Let's call this one T1, just so we keep that straight. Okay. T2 is T1 minus 0.85. All right. Anyone? Where do you go? Where do you go with this? That's exactly where I'd start too. Finding the time for the first one. Okay, let's say for the first one, D is equal to VIT plus 1/2 AT squared. Remember, this T that we're finding here is T1, right? Completely separate from problem number 2. Completely separate from the second ball there. VIT is 0 because VI is 0. So D becomes 1/2 of A times T1 squared. Let's rearrange it to solve for T. The 1/2 and the A go down by dividing. Delta D over 1/2 A. And delta T is therefore the square root of delta D over 1/2 A. So delta D is neg 60. Divided by 1/2 of neg 9.81. Square root that. Let's get this as a class here. Say neg 60 divided by brackets 0.5 times negative 9.81. And let's square root that. 3.4975. All right. Carrie, you didn't get an answer for this because you're right there with your method there. T2, let's get that now. T2 is 3.4975 minus 0.85. Let's get that value. $2.64. $6.475. So look at this. We've just found out how long ball number 2 falls for. 2.6475 seconds. Let's get VI. Okay, let's get VI. Let's do it over here where we have a little bit more space. VIT plus 1/2 AT squared. This time solving for VI. Okay. How do you get rid of, what do you get rid of first here, guys? Rule number 1, get it on the top. It's already on the top, right? Rule number 2, get rid of, Jordan? Get rid of what? What's not attached? What's not attached to VI here? What's not attached to the VI there? And 1/2, right? 1/2 AT squared. How do we get rid of that? No, it's added to it, right? So we get rid of it by, right. So it becomes D minus 1/2 AT squared equals VI times T. When I get VI by itself, now it's easy, right? Get rid of what is attached, get rid of the T. So we take that over by dividing. D minus 1/2 AT squared over T equals VI. All right, okay, moment of truth here. We had a couple people get different answers here. Let's see what we get. D was negative 60. Subtract 1/2 of negative 9.81 times the time of 2.6475. Square it over 2.6475 equals VI. Let's do this as a class here, and let's see if we get one of the answers that somebody had here. Okay, let's say neg 60, subtract brackets 0.5 times negative 9.81 times 2.6475 squared. Okay, and the brackets. It's divided by 2.6475. And we're going to get an answer of negative 9.7. That should be 3 digits, actually. Negative 9.68. Oh, nobody had that. Oh, so close. Nobody had that. What did you do for that question? Oh, so you did it all right, but you manipulated it wrong? Oh, goodness. Cost you a Slurpee. How does that make you feel now? My goodness. You could have had a nice ice cold Slurpee this afternoon when it's 27 degrees outside for free. Just because of algebra here. Jane, what did you do wrong? Oh, that's it? That's all you did wrong? Forgot to square root the time, another manipulation thing. Guys, in your algebra. You guys use this method though, hey? More or less? Good. Carrie, you were right there too. I'm not sure if you had an answer for that, but you were right there with the method. Does this make sense to people? Guys, I hope it makes sense, okay? We've just done 3 questions. All 3 of them are real tough questions, real challenging questions. If you didn't get any of the 3 of them, don't panic about that. It doesn't mean you're not going to do well in Physics 20 because you didn't get any of those 3 questions, okay? These are brain exercise questions, okay? These are meant to make you smarter when you see them gone over and you understand them, okay? It doesn't mean you can do them. It means you understand the logic behind them, hopefully. If you don't, come and see me. I can help you out with that, okay? Okay? Yep. 34. Okay, well, I think you are typing it in wrong. I'm not sure what you're doing wrong. I'll check there in a few minutes when you get working on some questions. But I can tell you that I don't know what, just looking at the question, I don't know what the time should be off the top of my head. But I know falling 60 meters is not going to take 34 seconds. Okay, it's going to take more in that range of 3 or 4 seconds. So I think my time would be the right one there. And I think you're just doing something wrong with the calculator there. I'll help you out there once, as you say, once you get working on some questions. Good? All right, you also had a few more questions that you were working on from last week, and that was on your velocity time graph worksheet. Okay, I'm going to show you some answers to those up on the board, and then we'll go over a couple of those questions as well. Question number 1, have a look at it. See if you got all the answers. Don't worry about how you did it right now, okay? If you struggled with getting an answer, just let me know and we'll go over that question. Don't worry about relying on what's up on the board. Look at the answers. We'll put up question 2 in a second. Question number 2, have a look. Have a look at question 3, please. Finally, guys, let's have a look at question number 4 there. Into those 4 questions we need to go over. 1, 2, 3, or 4. Oh, you got them all? All right, well, we're going to pick one then. Let's pick number 3. We'll go over number 3 as a group here, okay? Okay, number 3 gives us this graph that we see on the left-hand side of this page and asks us to find the velocity at 12 seconds. How do you find the velocity on a v versus t graph? Easy. 3 words. Who's got them? Up and over. Good. 12 seconds, we go up and over 5 meters per second. Good. The acceleration between 0 and 8 seconds. You can see in my solution here that I've calculated the slope between 0 and 8 seconds, right? Rise over run. The rise is 5 minus 0. The run is 8 minus 0. Rise over run works just fine to do that. What's the alternative, though? What's the other way we could have found the acceleration from 0 to 12 seconds? 0 to 8 seconds, I should say. Yep. Right. A is equal to delta V over delta T. Delta V would be 5 minus 0. Delta T would be 8 minus 0. So it would be the same thing as saying the rise over the run. Okay, we get the exact same answer, 0.63. The acceleration between 8 and 18. I don't even have any work shown for this one. Why is it 0 meters per second without any work shown for it? Okay? Right, it's constant velocity, so the acceleration must be 0. Now, if you wanted to show work for that, you could go rise over run, right? What's the rise, though? If it's a flat line, what's the rise going to be? Nothing, right? 0. So if the rise is 0, it doesn't matter what the run is. The slope would be 0. And finally, the displacement of the object. Here we've got 2 stages. Okay, here's a triangle, and here's a rectangle. We have to find the area of both of those. Okay, the first one is 1/2 base times height. Base is 8, right? The base of the first one. The height is 5. Second one is a rectangle. It's base times height. The base is 10. It goes from 8 to 18, so the base would be 10. You get a total area of 50 for that one. Add them both together, we get 70. What would have happened? Quick question. What would have happened if it had been like this? Lewis, what would have happened if it had been like that? We would have made it a negative displacement, that's all. Right? It means it was going backwards, which makes sense, right? If it's below the x-axis, the velocity is negative, so the displacement would have to be negative as well. Good there? All right.